Stars that we see at night are stars like our own sun that turn hydrogen into helium in their cores for the most part, and then a few other types of stars out there. Now that's a statement that needs some support. Actually, there's gonna be a lot of work done before we are able to support that outstanding claim that stars are similar to our sun. I'll remind you again that the distance to stars was done by method of parallax, kind of similar to what we've done in the very first lecture, establishing the distance to the moon and the sun. Then I will show you that some of the stuff we've learned about light, spectrum, etc. leads to what we call the main sequence on the HR diagram, the asymptotic branch, etc. Then I'll show you that temperature and mass may relate to rates at which nuclear fusion of hydrogen into helium happen, and that will not only support the claim that stars are like suns, but in a backwards fashion support the fact that the sun is a nuclear furnace. In the early 1800s, a guy by the name of Bessel gave the last resounding proof that the Earth goes around the sun. What he has shown is that from the picture in front of you, you can tell that you can see from the Earth the star that's relatively close moving relative to the background stars, and by that you can show that Earth moves. As a matter of fact, there are some stars that actually portray a circle in around the stars because they're close relative to the other stars. Same exact idea, only think about those stars that are above Earth's orbit and relatively close when you compare them to the very far away stars. Then it was very, very complicated to achieve such wonderful proof that the Earth moves. Now it's a little bit easier. In the 1990s, the European Space Agency launched a satellite called Hipparcos, named after the fellow that gave names to lots and lots of stars. Hipparcos is actually in a weird Earth orbit. One of the rockets that launched it failed, so it moves in an elliptical orbit. So it's not exactly in the orbit that we expected it to be, but it still manages to measure those parallax measurements incredibly accurately. The whole idea of science is that it can support results independently. You look at a star, nearby star, let's say Alpha Centauri, and you say, wow, it looks like the sun. Just the same color through a prism, just the same absorption and emission lines. And the question is it the same as our sun? We know now that the sun gives off 400 trillion watts. How much does Alpha Centauri does? Now that we know the distance using parallax, we can do just that. Use the slide underneath that explains that things that are further away are dimmer. Take the actual brightness of Alpha Centauri and just try and find out how bright Alpha Centauri should be from what brightness it has. And we find out, interestingly enough, that it has just the brightness of the sun. Whoa. In order to be a little bit more systematic in our studies of the stars, we are going to use a method of taking a light from a star, breaking it into its components. Using a prism, if you had no cold or cooler gas in the atmosphere of those stars, you would get a rainbow spectrum. But since we do have that extra cloud of cooler gas surrounding the star, we have a spectrum that you may see on the upper right hand side. If it was just the slightly cooler gas, you would get the emission line spectrum. Using spectroscopy in the late 1800s, Harvard-Smithsonian people figured out how stars should be categorized. They didn't quite figure how they work yet, but how to categorize was found out by Annie Jump Cannon, many women that worked for minimum wage at the time, Thomas Pickering, and later on Henrietta Leavitt. What they did is they looked at the spectrum and categorized it according to how the lines looked. Ends up that if the surface of the star is incredibly bright, such as in O stars, the atoms are so completely ionized that you'll have no lines whatsoever, and usually these will be the brightest stars. Of course, that depended on how close they were, but you can take that into account. So if you knew how close they were using parallax, then you could actually find out whether they're O, B, A, F, G, K, M, etc. Oh, be a fine girl, kiss me. Oh, be a fine guy, kiss me. These are mnemonics used over the years to remember the order of spectroscopy, but as you can see at the very top panel, this corresponds to temperatures. O is the hottest temperatures of the surfaces of stars, and M the least hot. Still 3000 degrees pretty darn hot, but not as hot. Absolute magnitude means basically brightness. So if we actually stuck those stars, including our own, which is smack in the middle, if we stuck those stars on this graph, then we would have stars that have high brightness, that's luminosity, low brightness, very hot, not very hot. You would expect that they would be all over the map, but they aren't. They're on a very narrow band called the main sequence, and then in a bunch of giants, and very few other stars here and there. That's a very puzzling result, unless we take into consideration more information. This is the same exact diagram, only simplified, and with fewer stars, and you can see that most of the stars are either bright and hot in their surface, or not as bright and not as hot, with a few off the sequence. Now, in order to explain that, we will need to tell just a little bit more about those stars on the main sequence, and in the next slide we will. Let's go back to the Doppler effect, that effect that we have used in the past to tell that there are other planets orbiting stars, or basically using Kepler's law, the fact that, for example, in the lecture last week, I left a result of one of your homework assignments on the whiteboard where I've shown you that when you have some orbiter around the planet, you can find out about the planet's mass by basically how fast it's moving towards you or away from you. Towards you, it will be blue shifted, away, red shifted. Now, use that to find the mass of some of those stars in the main sequence in that very narrow band that have partners. Ends up that half the stars in the sky have partners. They come in pairs, which is very convenient because now we can tell not just their temperature and their brightness, but also their mass. This is a spectrum from a so-called spectroscopic binary. What you will see is that in one picture the spectral lines are merged, and in one they're shifted. Let's see in the next 3 slides why that is. In this picture, one of the stars is moving towards us, and that is star A. and star B is moving away from us. Therefore, if they had the same exact lines, A would be shifted towards the blue, B would be shifted towards the red. In this picture, both stars move laterally, therefore they have the same exact spectrum. Here the situation is flipped. B is blue shifted, whereas A is red shifted. In the simplest cases, it is fairly easy to find what the mass is, especially if one of the stars is much more massive than the other. So for example, those blue stars are fairly easy to measure, to weigh. Ends up the blue stars are very massive, the yellow stars are not as massive, and the red stars are less massive. So now look at this HR diagram where you have not so bright, very red and low temperature and not so massive stars, whereas on the other end of the spectrum, so to speak, of the main sequence, there are blue stars with very hot surface, and they are bright and massive. I will tie this all together with a picture of how the sun works in the next lecture.